Okay, if you noticed, okay, we have had some probabilities, and one might wonder, okay, whether for some systems, if a particular saturation point or steady state point is going to be reached, and oftentimes the answer to that question is yes. And for what we have concerning steady state, okay, we have for what is referred to as finding the steady state matrix of a Markov chain. Again, first of all, you check to see that the matrix of transition probabilities P is a regular matrix, okay? And regular matrix meaning that either the probability matrix itself or a higher power of it can reach a certain state whereupon we have all the entries inside to be non-zero. In other words, to be all positive. And also it says to solve the system of linear equations obtained from the matrix equation, where we have P times x with the bar over it, which is in reference to the steady state matrix, is equal to the steady state matrix itself, along with the equation where we have the sum of x of 1 all the way up to x of n is equal to 1. And it says to check the solution found from this second step in the matrix equation, where we have again P times the steady state matrix X is equal to the steady state matrix itself. And looking at just some examples here. Okay, we can say that we have transition probability matrix, okay, which we had to be stochastic, and the sum of the values in the columns, okay, will be a 1, and here we have a regular matrix P, okay, since we have all positive values contained, and here we have 0.6, 0.2 for the first row, 0.4 and 0.8 for the second, and we're looking at determining the steady state matrix, okay, so we have x to the bar over it, and the number of elements x, we want to have it 2, so we have a 2 by 1 setup, and the sum of x of 1 and x of 2, okay, will be equal to 1. And looking at what we have with the steady state matrix equation itself, so you have P times the steady state matrix is equal to the steady state matrix itself. And so just looking at multiplying together, okay, so if we itemize, okay, so we have x of 1 times the first column of the matrix P, and then we have plus x of 2 times the second column of what we have for the elements in matrix P, and we have is equal to, once again, the steady state matrix itself. And just looking at the system that is set up, so we have 0.6 x of 1 plus 0.2 x of 2 is equal to x of 1. And we have 0.4 x of 1 plus 0.8 x of 2 is equal to x of 2. And just combining like terms and just setting the equation to 0. So if I combine 0.6 and 1 x of 1 in the first upon subtracting x of 1, so this first equation in the system is going to be negative 0.4 x of 1 plus 0.2 x of 2 is equal to 0. And for what we have in the second equation, if I deduct 1 x of 2 from both sides, I have in the rewrite 0.4 x of 1 minus 0.2 x of 2 is equal to 0. And again, we had the sum of x of 1 and x of 2 is going to come out equal. So we're going to have the sum of x of 1 and x of 2 equal to 1. And just setting up an augmented matrix. Okay, so you had the first column in reference to the x of 1 terms, middle column in reference to the x of 2 terms, and the last column we had the values to which each equation is set equal. And just looking at performing the Gauss-Jordan elimination. Okay, so if I rearrange where I had the bottom row at the top and just shift vertically, going from the first row to the second row to the third. And again, I want the first column to consist of 1, 0, 0. So if I take the second column elements and add 2/5 of the first row elements, I have 0, 3/5 and 2/5. And for the last row, if I take away 2/5 of the first row elements, okay, I have 0, negative 3/5 and negative 2/5. And then just continuing, and I want the second column to consist of 0, 1, and 0. And I can change over the 3/5 to 1 upon multiplying the second row elements by 5/3. Okay, so here I have in the middle 0, 1, and 2/3, and then changing the 1 and the -3/5 to 0. Okay, so we have for the first row, I'm going to take away directly the second row elements. So we have 1, 0, 1/3. And then for the last row, I'm going to add 3/5 of the second row elements. So we have 0, 0, and 0. And for what I have here for this reduced row echelon form, the 1, 0, and 1/3 is in reference to x of 1 is equal to 1/3. And then we have 0, 1, and 2/3 will be in reference to x of 2 is equal to 2/3. And so we have for the, what we have in the case of what we have with the result that we have for the steady state matrix, we have, again, you have x of 1 and x of 2, where x of 1 is at 1/3 and x of 2 is at 2/3. And you could also put this in transpose, where we have 1/3 and 2/3. Okay, and now let's say that if we have what's going to be a 3-equation system, okay, and we have for another regular matrix, and we have a 3x3 arrangement. And again, for the steady state matrix, okay, we'll have 3 elements with x of 1, x of 2, and x of 3. And again, the concentrations will add up to 1. So you have x of 1 plus x of 2 plus x of 3 is equal to 1. And just going back to the steady state matrix equation, okay, so you had the transpose probability matrix times the steady state is equal to the steady state itself. And so just looking at the interaction and itemizing, so you have x of 1 over the first column elements from the transpose property matrix. Then you have plus x of 2 times the transpose property matrix's middle column elements. And then you have plus x of 3 times the last column of the transpose property matrix. And again, we have is equal to what we have with the steady state matrix elements. Okay, so just looking at setting up the equations. So what I'm going to do here is that for the first, I'm going to combine the x of 1 terms. So 2/5 of x of 1 minus x of 1 will be -3/5 of x of 1. And then we have plus 3/10 of x of 2 plus 1/2 of x of 3 is equal to 0. For the second equation, I'm going to combine the x of 2 elements. So I have 1/5 x of 1 minus 4/5 of x of 2 plus 1/10 of x of 3 is equal to 0. And then for the last equation in the system, I'm going to combine the x of 3 terms and set this equal to 0. So we have 2/5 of x of 1 plus 1/2 of x of 2 minus 3/5 of x of 3 is equal to 0. And once again, we have the sum of x of 1, x of 2, and x of 3 will come out to 1. And from what we have here, I'm going to set up with the x of 1, x of 2, x of 3 coefficients, as well as the constants to which we have each equation set equal. I'm going to form an augmented matrix that will be 4 by 4. And so for what we have in this one, and I bypassed all the steps here, but for the reduced row echelon form, okay, we want to have for the first row, you have 1, 0, 0, 0, and then 43 over 101, and that would be what we have for x of 1. And the second row we have 0, 1, 0, 0, 16 over 101, and that's going to be the level for x of 2. And then we have 0, 0, 1, 0, 42 over 101, and that is going to be in reference to x of 3. And again, at the last row, we have zeros across. Okay, so we do have consistency. And so for the steady state matrix, we come out to where, again, we have with x of 1, x of 2, and x of 3 lined up, we had the respective values of 43 over 101, 16 over 101, as well as 42 over 101. All right, now going back to the earlier problem, when we were looking at transpose probability matrices and looking at what we had a while back with the Coke and Pepsi restaurants example. And again, when we had looked at just projecting using Markov chains, okay, again, we originally had 10,000 restaurants, 5,500 of which served Coke, 4,500 serving Pepsi. And we said that there was a 20% chance that the restaurant serving Coke would switch to Pepsi, and a 10% chance that those serving Pepsi would switch to Coke. And we have how many restaurants would be serving each beverage in 1 year and 3 years. And going back, so after 1 year, the number of restaurants serving Coke had dropped rather drastically from 5,500 to 4,850, whereas in the case of the restaurant serving Pepsi, there was quite an uptick all the way out to 5,150. And then we have after the third year, the projection was for Coke, you have 4,077 restaurants, so you have another precipitous drop. And for Pepsi, you have another substantial increase where we have right at 5,923. And so you have a sharp decline in the number of restaurants serving Coke, and a rather dramatic increase in the number of restaurants serving Pepsi. And one might pose the question, would there be a saturation point, like a theoretical maximum for the number of restaurants serving Pepsi in the pool of 10,000, and a theoretical minimum for the Coke serving restaurants? And the answer to that question is yes, if you go by the use of Markov chains and using the steady state matrix. And so we have posed the questions. What is the steady state matrix, and how many restaurants for each category will there be? So looking at, again, the steady state matrix equation. Okay, so you have the transpose probability matrix times the steady state is equal to the steady state matrix. And again, we had the transpose probability matrix at 0.8, 0.1, 0.2, and 0.9. And then just setting things up. And again, so you have from the steady state matrix, you have x of 1 times the first column of the transpose property matrix, and then you have plus x of 2 times the elements of the second column from the transpose property matrix, and we have is equal to the steady state matrix elements. And so we have setting up what we have now. We got 0.8 x of 1 plus 0.1 x of 2 is equal to x of 1. And we have 0.2 x of 1 plus 0.9 x of 2 is equal to x of 2. And for the first equation in the system, I'm going to combine the x of 1 elements and set the equation to 0. So I have negative 0.2 x of 1 plus 0.1 x of 2 is equal to 0. And for the second equation in the system, combining the x of 2 elements and setting that equation to 0, and we have 0.2 x of 1 minus 0.1 x of 2 is equal to 0. And again, just for the sum of x of 1 and x of 2. Now, x of 1 is in reference to the weight involving the Coke serving restaurants, and x of 2 for those serving Pepsi. And so we have x of 1 plus x of 2 is equal to 1. Okay, where 1 is like in reference to 100%. And taking what we have for this modified system, and I'm going to set up an augmented matrix. So we have corresponding, negative 1/5, 1/10, and 0. And for 0.2, negative 0.1 and 0, I have 1/5, negative 1/10, and 0. And again, 1x of 1 plus 1x of 2 is equal to 1. And for what we have in the case of the reduced row echelon form, and we have 1, 0, 1/3. So x of 1, which would be in reference to Coke, is going to be 1/3. And for 0, 1, 2/3, that signifies the x of 2, which is in reference to the restaurant serving Pepsi. Okay, we have it 2/3. And so for what we're going to end up with is that for the steady state matrix, okay, we have containing x of 1 and x of 2. And so this reaches out to the 2x1 matrix where x of 1 is at 1/3 and x of 2 is at 2/3. And with 1/3 in reference to Coke, we have out of the 10,000 restaurants, those serving Coke, okay, we'll reach that theoretical minimum where we have to the nearest whole number, we have at 3,333. And for the saturation point in terms of how many out of the 10,000 restaurants, assuming the same consistent trends throughout, will serve Pepsi. And so you have 2/3 of that 10,000, where we have right at 6,667.